Thank you for the introduction. The topic today is crack initiation. So we have two different parts there. So the presentation is distinguished into experimental crack determination, how we do it, and then the second big part is the prediction or the statistical or the analytical calculation of the crack initiation with a straight crack front and with a semi-elliptical crack front. And at least I will give a short conclusion about this. Maybe some of you have already seen this slide, which my colleague presented yesterday. What we did here, we have a bending experiment, so bending specimens, and tested two different notch geometries. The mouth notch here, with a depth of 4 mm and the width of 2 mm, or the notch radius 1 mm, and the sharp notch, where the depth is 4 mm and the width is 0.4 or the radius 0.2 mm. We tested both geometries with a load ratio of 0.1, and every geometry or both geometries on different load levels or different load ranges. So we have the information about the load and the information about the number of the cycles. What we need is the information of the crack lengths. This is plotted here on the right. How we did it with this DCPD method, direct current potential drop method, to have also the information about the crack length. So, and what is the idea behind? We can see it in this sketch. The red line means the crack length. So the crack will grow or start to grow at a certain point and grow then until it fractures. So we can distinguish the lifetime of the specimen into a crack initiation period and a crack growth period. Here is written, or we assume that the crack length of 20 microns, when the crack is 20 microns long, the crack is initiated. This has two reasons. One is the measurement accuracy, and another one is we tested the pearlite material. And this is exactly the size then, or about the size of 20 microns, where the pearlite colony, or the size of the pearlite colony. Okay, and we tested those geometries here with different load ranges, as I said, and plotted then the stresses in front of the notch in the diagram, in the double logarithmic diagram, what we can see here then. So on the upper one is the mouth notch with the radius of 1 millimeter, and the sharp one is 0.2 millimeter. If we take, for example, the mouth notch, we can see here the distinction between the crack initiation, which means here the green line, and the failure one, the red line. The crosses means all those experiences, and we clearly can see there is a difference, or there has to be a difference, or the distance between those lines is exactly the crack expansion period, or crack growth period. For the sharp notch, the crack initiation is a little bit earlier compared to the mouth notch, but also the crack growth period is longer. So that's all about the experiments, but what is the idea now behind to have a calculation, analytical calculation, to can predict, that we were able to predict the crack initiation. I will start with the straight crack front. Again, the slide. And what is the idea now behind? It's very hard to say, okay, how big is the failure at the beginning? So the idea behind is to use the information about the crack lengths and the number of cycles, or especially the crack lengths, and using doing this with a backward calculation exactly to this point here, where the crack length is 20 microns. What we need for this calculation is the information about how the crack grows. So this means the NASCAR equation. Don't be scared about this slide. It's a little bit overloaded, but I briefly will explain it. We tested commonly used fracture mechanics single edge notch bending specimens to gain for different stress ratios or load ratios the behavior of the crack. So we tested it at load ratios -1, 0.1 and 0.7. Here in this diagram we can see the crack resistance curve, what we need to describe the short crack growth behavior with this equation and the exponential function behind. The dashed lines mean the coefficients of variation, what you heard yesterday from my colleague, of the statistical analysis. And what we need also for long cracks is the behavior the behavior is described then by using the NASCAR equation, what you can see here, also for the different load ratios. So why we need the different load ratios? Some of you maybe think, okay, the specimens were tested at load ratio 0.1, so we don't need it. But if we study in detail in front of the notch how the stresses behaved, we will see why we need it. So this is exactly then the next slide. It's very hard to gain it from experiments, the stress in front of the notches, so we did numerical simulations of those two different notch geometries and evaluate then the stress ratio in front. Here we can see that those two curves for the different load amplitudes for the mild notch and here for the sharp notch. Both start at minus, and then after a certain distance from the notch it goes back then to the load ratio of 0.1. What else we need? So the crack doesn't start on the surface, it starts from a notch. So we need a different geometry function, and we use the approach here from Neuberg, where it's included here in the stress concentration in front of the notch, the geometry of the notch, and we can see it here for the two different notch geometries. The red one means the sharp notch here, where here is the distance on the horizontal axis, the distance from the notch, and here is the geometry function y. And the blue one means the mild notch with a radius of 1 millimeter. So, and with this information, the short crack behavior, the NASCAR equation, the different stress rates in front of the notch, and this geometry function, we can then calculate from the point where it fractures and the backward calculation, and can then estimate or predict when the crack initiates. We exactly can see here in this diagram then the difference. So we have the difference between the experiments and the prediction. On the horizontal axis, we can see the determination of the crack initiation from the experiment, and on the vertical axis the prediction by using the backward calculation. I will take an example. If the experiment is 100,000 cycles, we go up this line here, and the prediction should then be also 100,000 cycles if the prediction works 100% well. So this means exactly this black 45-degree line. And the dashed lines means the scatter band of minus and plus 20%. If you look, for example, to the sharp notch here, it works quite well. So the prediction compared to experiments works quite well. If we take a look for the mild notch, the difference from the circles and the crosses means just the different statistical analysis or the coefficients of variation from the statistical analysis. And here we can see the upper coefficients of variation, which means the red crosses works better for this. But in general, what we can see, the prediction and the backward calculation works quite well to get the same point of the crack initiation. But what we saw, I told you before, we take the limit or the border for the crack initiation of 20 microns. So we stop exactly the crack with a crack length of 20 microns and break it in with liquid nitrogen, and we saw a semi-elliptical crack fronting. So this means the crack initiates with a semi-elliptical form and then grow after a certain length where the crack is straight or the crack front is straight. This brings me to my next topic. So, in this diagram, there is the comparison between a straight and a semi-elliptical crack front. We have to start at a crack length, a start called here, by using here just for example the intrinsic threshold of 2.5 megapascal square meter, and here we can see then the comparison. The green line means the straight crack front. It grows very fast until it fractures, and the black one means the semi-elliptical crack front. So it's not that fast, and the difference or the number of cycles in between is very big. But with in comparison, the blue one means one measured experiment. With the experiments using this direct current potential drop method, we cannot distinguish between a straight or a semi-elliptical crack front. So we have to transform the semi-elliptical crack front in a straight crack front to be able to compare it with the experiments. And this is done by using an equivalent area of the crack front. And this is exactly then this red line. We can see in comparison with the results, the red line and the blue one. The blue one is the experience, and the red line, the transformed semi-elliptical crack front, really fit very good together until this point here. Here the slope is different, and the grade of the blue one and the green one is from this point similar. What does this mean? This means exactly, or we suppose, assume that this is the point where the semi-elliptical crack front transforms to a straight crack front, and then at this point we have to calculate with a straight crack front to the end where it fractures. This has been done for the two different notch geometries and the different load amplitudes, and we can see here the results. So the full line means the experimental measured data, and the dashed one, the calculated one. And we can see that it fits very good together for the most of the specimens. But the crack starts very early and not as assumed in the first task after a certain number of cycles. So now this brings me to the end. To the conclusion, we showed that it is possible to determine experimental the crack initiation, and we also find a way with the backward calculation to predict the crack initiation point, and it fits very good within plus minus 20 scatter rate. But in reality, the crack doesn't start with a straight crack front. It starts with a semi-elliptical one, and by using this one, we have to transform it into a straight crack front to compare it with the results. And what we saw is that the crack is initiated very early and grows then in a semi-elliptical form until it fractures. Okay, thank you for your attention.